Okay, all right, let's go. So this section on power law mechanisms, so we're going to finish up the stuff that's randomness and this variable transformation story. And then we'll move into some of these kind of ubiquitous generative mechanisms, right? How things are made. So I like to think it's generally true of most of the sciences, that they care about how things become things, right? Physics is all about how things become things. You know, evolution is a becoming story. The people who don't care are mathematicians, right? It's just all true. You know, there's this idea of the book. God has this, God has this book, and you're simply opening up the pages, and that's it. Right? So it's just all true. You're just lifting up the tiles and finding your theorems. So, and there, there's a deeper aspect of that. Okay, so I was going to show you this, so I put it in the right place. So this is what you guys ended up with. I didn't have it in the slides the other day. So this is the average of what you collectively thought was the correct thing. And it's just a straight odd average, I suppose. But yeah, so it's 85%. 85% was the real one. So, you were a bit below. Even though you're all very clever and you know what's going on and you understand these things, it's still hard. Although, big range of guesses. Yeah? So there's we have a king and everyone else is a peasant story. And there were some of these issues with the quintiles have to go down. So there was a little quirk there. But generally speaking, this is a very nice, optimistic, more than north of Sweden sort of situation. Maybe Svalbard or something. I don't know. Polar bears all have about the same amount. And then this is your ideal. This is where we see what you guys think about how the world should be. So economists are usually more of these kinds, right? So, but yeah, a big spread again. This is the everyone should have the same is right there, and this is there should be another group of humans situation. We give something to someone else. I don't know, polar bears maybe. All right, so. There you go, and that's, so there's the previous ones. Obviously I had more students. What have I done? All right, okay, so you can look at those. It's in the appendix on that one if you want to ever come back to that. So let me see, I want to, we left in the middle of the big end and I didn't quite do it properly. Okay, so first return problem. Oh, yeah.
When should we do our post-presentation notes?
Yeah, usually it's about 6 weeks in, and there's some problem with me organizing myself to, I have to stop talking. So, but yeah, usually 3 or 4 weeks. Okay. So we can talk about, I was going to give you some suggestions probably on Tuesday. And I said, if you want to work on some of this, any data set or any problem you want, of course you can do that. But we also have some things we can share with you, like 10% of all tweets, which is an interesting thing to play around with. So there's that. Okay, let me plug this in. Projects are fun, really fun. That's a sad, it's not even spinning. How long has that happened? Oh. Is it, okay. Okay, just, okay. Oh, it's your idea. Steve Jobs. Better be a good new iPhone. All right, so let's see. We went through this argument about what's the probability that it will take n steps for a walk to return to the origin. Okay, we got to this end and I kind of didn't give you the full story. So let's start off with the big shebang. You will determine that in fact the form behaves like this asymptotically. So our friend pi appears again, just because it likes to be involved with everything. And there's some other aspects in here, but really it's this end of the 3 halves. That's the big deal. So it's a probability that you return after n steps. It's decaying like n to the minus 3 halves. So our gamma, we've defined it as something to the minus gamma typically, so it's a minus 3 halves. So let's look at this. So if we normalize it, after n steps, so we said t equals 2n, so after 2n steps, so how many random walks are possible, right? 2 choices, then another 2 choices, another 2 choices, another, right? So it's branching exponentially, you get 2 to the 2n choices. So there are 2 to the 2, we had this before, there are 2 to the 2n paths. So we're gonna have to divide out by that piece. So that's the total number of possible paths. We divide out, and there's a 2 to the minus 3 halves left there, and it looks like we have a root 2, so we could stick those guys together. Okay, so we're dividing by 2 to the 2n. So these guys are gonna cancel here. And we end up with, okay, that's a sneaky thing we can do. So we'll take 2 to the minus a half and put it down the bottom, so it's just a root 2. There's a root pi was floating around. Sorry, we already have the root 2 pi. We have 2 to the minus 3 halves. We can join that up with the end of the 3 halves. So that's what I'm trying to say. So 2n to the minus 3 halves. And that's good. 2n was our t, right? We said it has to be an even number to come back, so we started to talk about t equals 2n. So we get back to, and of course we can have any constants in there, but this is really t to the minus 3 halves, and this is really 1 over root 2 pi. It's asymptotically that, right? I mean, you could just leave as a constant times this, but we in fact get this formula out. So it's quite a remarkable, strange business, right? It's just random walks. They shouldn't be very interesting unless you're gambling. At some point in Las Vegas, right, they transferred to, or they started to build machines that you could simply push a button, or you put your credit card in, and you could watch the thing go, right? You don't. So first of all, you had to pull something, right? The one-armed bandit, you actually had to pull something. You had to be involved in it, and then it just became a button, and then you could go away from that altogether and just put the card in and watch. And that's interesting enough. As it is, apparently. Anyway, yeah, voluntary tax. Okay, let's see. So t to the minus 3 halves. So that's a very interesting exponent. So here it is. We have gamma equals 3 halves. You can talk about, there are all sorts of interesting variations. We've just done a little simple up and down, probably of a half business. It's on a discrete lattice. You can talk about continuous time and space walks, Wiener processes, so Norbert Wiener. Not Anthony Weiner, different character. Norbert Wiener did not take pictures. He was a very famous mathematician, applied mathematician, generalist at MIT, actually. So he did this very nice work for continuous processes involving noise. All right, so we can generalize to that. That's just a note. It's normalizable. You will have just done this in your assignment, right? So gamma has to be greater than 1. It's not integrable otherwise. So we've got 3 halves, so it's okay. So normalizable means that with probability 1, it comes back, right? We have a decent probability distribution. So the walker will always come back. So that's sort of a first basic question. But the mean and the variance and all the higher moments are infinite. And we actually, we don't have an upper bound here. This is a random walk. It's in principle infinite. So that's crazy, right? It's a hashtag. So it will take on average, even though, what did we say the other day, half of them come back straight away, right? Maybe I should use zombies. Okay, so, you're nucleating zombies at the ground zero, and they're going out. 2 of them they'll come straight back, right? And the other ones will pop off that way. So half of them already return, and then they keep wandering and wandering. You keep making them. You can think of it like that. Walker, see? Yeah, right. So they will come back, but on average, it's going to take an infinite amount of time. That's a very strange distribution. It's not your normal distribution anymore, right? It's not your parents' distribution, but it's reality's distribution. All right. So you shouldn't gamble against someone who's got lots of money. If that wasn't already obvious, that's a bad situation, right? And I remember a friend of mine figuring out this in college, that you simply have to double your bet, right? So you're on roulette or whatever. And of course, it's not quite 50-50, but you lose, and then you just double your bet. You keep doubling your bet, keep doubling your bet. And eventually, you get $1 because you win. However, if it goes all blacks and you've been betting reds the whole time, it doesn't work out. All right. pretty smart guy, but I don't think he ever tried to do that. All right, so shouldn't do it. Higher dimensions, you're very keen to find out, right? I know, so this is, this has been a game, it's kind of an interesting thing, sort of surprising it comes out of such a simple story. D equals 2 dimensions, and so a whole extra complication, right? And I'll say this a bit, I'll repeat this probably, but it turns out that D equals 1 is usually pretty easy for solving problems. It's usually not very interesting, although it is in this case. And I'm talking about all kinds of problems. D equals 2 dimensions. Often that's where you start to get into horrible mathematical complications and interesting things start to happen. D equals 3, even worse, you can't solve it, typically. And then often you get a break. So D equals 4, 5, 6, it starts to look like it's basically an infinite number of dimensions. And so there's usually what's called an upper critical dimension to problems. It might be 6, it might be something ridiculous like 4.5, because we can have that. But above some dimension, called a critical dimension, everything kind of looks like a monstrous mean field thing, which means that everyone is kind of, say you've got agents, they're all communicating with each other. They're not really in a structure anymore. And then it's easy to solve. So it turns out we live in kind of one of the most difficult kinds of physical spaces, 3 dimensions. All right. Okay, so it turns out that as soon as you go up to 3 dimensions, the escape probability becomes non-zero. There's a chance it won't come back. And we're not going to do that. We just touched on this problem. In the assignment associated with this, I mention all of it, because these random walks, these first returns, they're pretty interesting things, right? So it turns out that there are all sorts of problems that kind of look like this. It looks like a partition from this side. There are many, many combinatorial problems that are related to what seems like a very simple, specific thing. All right, fine. So that's true. So you can actually determine these things. In fact, here, let me show you. This is pretty silly. Where's my thing? Oh. Okay, it doesn't want to show me the mouse. My bad. Yeah, so you can go and read about it here, and then there's a link to, where is it? My fault, I shouldn't have done that. High dimensions, blah, 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 blah. Yeah. So the math gets a little trickier. So this is a probability that you return, probably that you return in 3 dimensions. It's 1 minus this quantity, so it's about a third, 0.34. And this ridiculous thing on the bottom here is root 6 over 32. There's a pi cubed, and then gamma of things like 7/24 and 11/24. I mean, it's an exact result, but lots of monk deaths involved, right? So don't worry about that. We're not going to do that. But the big deal is it does not come back. Okay, so fine. So what if we just have a finite space and we've got a random walker wandering around on a finite space? We can think about that. So it turns out then that you actually get so you imagine you just have a square, and the random walker is wandering around. Some little complications to this, but basically it will reach each point with equal probability. There's a small tweak, and I'll get it in the network story here. And you talk about these probabilities in general as the invariant density of a dynamical system. So in the long run, where does this thing, you randomly sample the system at some point in the long run, all the transients have gone. What's the chance it'll be in a particular place? Well, so we turn this dynamical system into a geometric story, right? So we're just now looking at a probability on a space. So we get invariant densities in chaotic systems that are interesting and crazy, the strange attractor story, right? Things go everywhere. So on networks, which we'll come to later, complex networks, giant thing, we'll come to this later on. So a random walker wandering around a network, there's, so it's a simple network we're thinking about here. Every link is kind of the same flavor. If you're at a node, the chance you go to any of the nodes around you is equal, right? You're a random walker, you just lurch in one direction. It turns out that you actually don't end up in the same way, that you don't get this nice soup thing here. You end up in and it's a nice little mathematical calculation, you end up at nodes with probability proportional to the degree, the number of friends the node has. And so what's really happening is that the equal probability is actually in the edges. So if you sample, if you want to figure out what's the probability that a random walker will be at a specific edge, that's even. That's where, so it's edge space that you get the equal probability in. So that's a nice thing to realize. So that's actually happening in these normal spaces as well. It's just that they're lattices. So the edge space and the node space have the same structure to them. That's a beautiful thing. We don't have to worry about that too much, but we'll get to that. So it's actually, yeah, right. You know, and this matters for things spreading around, right? Lots of things spread around, diseases, ideas, the bucket thing, you know. So spreading on networks is a big deal. We'll get to that. All right, so I want to go through a little example of a model of a real phenomenon, river networks, which is, you know, so the big story. If you look geomorphologically, you have things being pushed up, and then you know, mountains being made and things being slurped down into the sea and all this sort of business. But on top of that, you get this river network structure, and that is, you know, great interest in general, and we worry about on Mars and whether there was water and all those sorts of things. So here's a very simple model for networks, and it turns out to have not the right statistics of real ones, real river networks, or basins, but it has the right, the way things connect with each other, the so-called scaling relations, match up. So it turns out to be a very useful toy model. So very simple, it's a triangular lattice, and at each point, fluid flows either of one to, right? So you flip a coin. So that's what's happening here. So we flipped a coin and went this way. At this point, we flipped a coin and went this way. And then so it starts to form a basin. So there's a basin. So if you map back up here, there's a little river basin here, and a little river basin here. And so they have, and if you think about their boundaries, they have random walk boundaries. So then it becomes analogous to this first return problem, almost, because you've got two random walks and they have to collide. And that's when the basin stops. So one question is, what's the distribution of basin sizes? You know, what's the structure of these real networks? And okay, so we've got that story. So as I said, we've got two random walk boundaries. So what can happen is, I really kind of want to do this just for my own amusement. Sorry. Super wrong. Is that good? Yeah. All right, so let's see. So yeah, you've got these two random walks, right? And then, go away. And then, so another one starts off here, it's random walking, and eventually they're going to hit each other. And in principle, they keep going, right? So this is the area we're interested in the middle. You subtract one from the other, and so this is a +1, this is a -1, roughly, right? So then we subtract, so this is walk 1, and this is walk 2. So 1 minus 2 is going to have this kind of structure. It's going to have some pieces where they both went the same direction, they both went the opposite direction, so it's going to be kind of a random walk which has these quiescent phases. But it's still going to be a random walk. Okay, and then we're asking the same questions. When does it come back to 0? Right? So when does this walk subtracted from this walk equal 0? Okay, that worked. Okay, so now we have, so probably 1, they both, we can renormalize it, right? So they've walked away from each other, that happens a quarter of the time. They've walked towards each other, that happens a quarter of the time. And then they've either walked the same direction this way or this way, and that happens a half the time. So we can make a version of a random walk. So we can really just ignore this part, and the main thing is here, right? Nothing's happening in here. In a sense, we can just sort of double the time it takes to get somewhere. So it's a random walk with pauses and probabilistic pauses. And it's, again, a first return problem. So already we have something here, right? We can say if we looked at this great big landscape now with this generation of networks, then the probability that a basin length, so we go to an arbitrary point and we look at the basin that it's part of, right? So we go up and we find where it ends, then the probability that it's part of a basin of length L is proportional to L to the minus 3 halves, because that's our story. Some factors, ignore. So that's weird. That's actually a kind of an odd thing. It's a very, again, you expect these basins to be infinite, which is a strange business on average. And for real networks, we see the same thing, actually, right? They're more complicated. They don't all go in one direction, so there's a directedness to this. But we see that same scaling. So let me connect a few other pieces in there. So we've got length. We can think about what's the area. And then there's all this branching architecture, which I do talk about in complex networks on a section on branching networks, which is a much bigger thing, right? We're sitting here with branching networks inside us, right? We've got the blood network story, which turns out to matter. We'll come back to that later on when we go into this theory aside thing. So if a basin's got a length L, its typical width is L to the half. This is the random walk business, right? So we know the standard deviation grows like L to the half. So that's a rough, this is a physicist comes in and says, right? Back of the envelope thing. So the area is A, it's going to be roughly the length, roughly the width, multiplied together, so it's L to the 3 halves. So we have a connection between area and length, and we can do something which we'll come back to later on, just a change of variables in a probability distribution. Very important thing. Probably done it somewhere else, but it turns out to be a very important thing. It's in the next section, actually. So L is proportional to A to the 2/3. We can turn it around like that. So we can just get the little differentials and figure these guys out. So if we take DL, and dA, then we dA to the 2/3, right? So dL is d blob here. So we differentiate that, we get 2/3, a to the minus 1/3 dA. So this is the Jacobian, this is the way we can transform between these two probability distributions because we need this, right? So we need, in general, you need py dy equals px dx. Right? You have to connect those things. Some other tricks if it's a non-trivial relationship between them. That's basically the idea, right? So area grows, length grows. So probably of ADA is probably LDL, and we know what this is. This is L to the minus, it's proportional to L to the minus 3 halves DL. So we can get P of A because we're going to start messing around with things. We're going to replace the DL as well by this beast. And so the DL gets replaced, the L gets replaced by A to the 2/3. So let's put that in there. A to the 2/3, this is L to the minus 3 halves, gives us just A to the minus 1. We get this extra piece from the differential. So a to the minus 1, a to the minus 1/3, it's a to the minus 4/3 dA. So that's nice. It's a non-trivial kind of exponent. Again, it's one that's between 1 and 2, so infinite mean, but it's certainly a decent probability distribution. But a nasty one, this is even closer to 1. So the mean is more ridiculous. So in general, it's a to the minus tau for real ones. So there are a couple of things we can prove to ourselves, and I won't necessarily do it here. Let me give you some real numbers. It remains a bit of a mystery as to why real, it's a big problem, why real river network basins have these distributions. There's a lot of arguing about optimality and randomness, which we're going to talk about very soon again for power laws. It's a big tension. Obviously, both things are probably involved. So usually you see in between 1.3 and 1.5, and now we had 4/3. It's not far off for the random one. But instead of 3 halves, it's usually more up towards 2 for gamma. This is the length distribution, the area distribution. But you can just look at these and you say, okay, the first thing you feel about these, right, is they're between 1 and 2. So that tells you something straight away. If an exponent is between 2 and 3, it's got finite mean and infinite variance. And it might be, infinite variance because there's an upper size. But you get a feel for those things straight away, right? If someone says, I have a distribution between, it depends what you want to do. If they want to pay you money or something based on a random draw from this one, you want the exponent to be less than 2. That would be good, yeah. All right. So there are all these scaling laws in river networks, and they're named after people who came up with them. So Hack's law, it's from 1957, length is proportional area to the h. So we just had 2/3, of course, for these random ones, these Scheidegger networks, which is 1960s. So for real large ones, you actually start to see it's more like a half. And that starts to make sense dimensionally, right? This is meters squared, so it actually becomes kind of reasonable. It's possible that for smaller basins, h is greater than a half, which suggests that as you compare basins, we'll come to scaling later on, that they stretch. Right? So if you want to take a little basin and stretch it to match a big one, you'd have to stretch it more longitudinally than widthwise. Okay. Certainly we have models where we're away from a half, like the one we just showed you. And I'll show you this quickly. You can redo all this calculation with this h here, which I just showed you was 2/3. We can keep things in an abstract fashion, so we can just flick through this. So if we had all of these relationships, we can connect these two distributions because we have the connection between their variables. So this isn't hard as long as you become au fait with how probability distributions work. So DL, again, we had this before it was 2/3. Now we have h, a to the h minus 1. And then you want to connect these exponents. That's the game. So these are called scaling relations. Again, it looks exactly like what we had. P of ADA, P of LDL, which just by assumption is L to the minus gamma DL. And we're going to stick in what A is in terms of, what L is in terms of A, and then the differential, how it changes. So A to the H minus gamma, so these guys are going to multiply each other, and then we're going to add H minus 1. So if you combine all of those together, you get a minus 1, that's this piece. There's an H gamma, that's this piece. The minus sign is out here. And there's an H here, and so we can put it here, and it's minus 1, so it's plus H. So that whole blob there is A to the minus tau. Crazy, right? So now we have a connection between these guys. That's general. And so it works for the random one, as we talked about. For the random one, we had 4/3, 2/3, and 3/2. So 3/2 minus 1 is a half. 2/3, so it's a third, plus 1 is 4/3. So that's good. But it turns out that real river networks don't have those exponents, but they do satisfy the scaling relation. So that's a nice story. And there are about 10 others that all can be expressed in terms of one or two of these other exponents. So that's an important thing. They're called scaling relations. You find this in all sorts of systems, fluid mechanics, lots of physics kinds of systems, but also biology where there are exponents and also things like Moore's law, for example. I mean, things in computational systems that get bigger and bigger. Any of these systems where there's some kind of scaling, one thing to look for is these scaling relations. Okay, just an important thing to know. And more work, you can't do it from what we've sort of assumed already, but it turns out there's a reduction here. It's not just 3 connected with one algebraic equation. Tau and gamma can be expressed in terms of h, or whichever combination you want to do it. So another thing is, tau is never the exponential of h or log of h or sine or anything crazy like that. They're always simple algebraic relationships, which should sort of make sense from a scaling point of view. Things are scaling, you're dividing things through, so they should just kind of add, subtract, and maybe divide. Again, always true. Okay, so as I said, this is an aspect. You've got a complex system. This is a way of simplifying its description. I mean, it's understanding the thing. You usually should see this wherever you have power laws. And when we're talking about this word universality classes, so this system belongs to some universality classes. It's the same as some other kind of system that might have different microscopic elements. These scaling things are the ones that define the class. And so we can say after a while, well, all right, H is the business. We're just going to measure H about our systems. And we'll measure them all, but H will be the thing we'll kind of try to connect things across, if we think it's the more fundamental exponent. All right, that's a good sort of side piece. A couple of other things to say about random walks. So that was all random walks. And in a sense, when we moved away from when we moved to general tau and general gamma, these general, I know gamma's being used twice, but this is just to connect you to the literature. When we move away from random walks, we're starting to look at some other fractional Brownian motion. Okay, so you can have these other pieces. So we'll talk about those. This is an example of actually just using again random walks. So it's a Ruin kind of story, and there's a citation to this paper. I think it's in PNAS. It's actually an old colleague of mine. I can't get my little, oh, there it is. 10, yeah, Whites and Fraser. So Fraser's at, come on, where's the little mousy thing? Okay. Can I just not see it? Is it there? No, that's bad. Is it there? I don't know where it is. Okay, sorry. Oh, spinning ball of death. Yeah, it's about mortality, right? So what's probably of not making it? Gosh, it's having trouble. So you start with some health at time t, and then you have a random walk after it. This is not a good way to live your existence, but it turns out that the kinds of distributions that you end up with, which is a modification of the one we're talking about, because it's what's called a first passage time. Instead of a first return, you're heading towards some point, which is 0 here, right? Your life is running out. If you look at stream, so again, it's a fluid thing, and you look at, so there's some good thing or bad thing that's being dropped into the stream, further up, then the way it spreads out, it doesn't all come down in a lump, it spreads out tremendously, and you get these power law distributions as well. Okay, so these guys, fractional Brownian motion. So this is a way to get these kind of weird distributions. And I'm just going to say this quickly. There's a ton of work on this. Different kinds of names. So you'll see fractional random walks, fractional Brownian motion. Levy flights is another version of it. There's a classic work, Montrell and Schlesinger, on 1O-F noise, and it's PNAS. Now, wow, this is 32 years ago. And it's just investigating all of these distributions. So one thing that's important is before we had the standard deviation is growing like t to the half. The big departure you get now is alpha can be greater than a half, we call it super diffusive. Alpha is less than a half, we call it subdiffusive. So this is this happens in a lot of systems, right? Even how money moves around the US, for example, you have to think about this kind of behavior. And these terms are used very widely. So diffusive just means random walks, what you get for free kind of things. Things are just randomly walking around. Super and subdiffusive are departures from that. So it turns out to make a random walk, we just had to flip coins. You had to remember where you were, but from that you just wandered around. So now to make your decision as to where to move next, you actually have to remember where you've been. You have to have a kernel that's remembering everything, right? So the simple mechanisms to produce these kinds of fractional Brownian walks involve memory. So that's this either way, subdiffusive or superdiffusive. So that's an important aspect to think about there. Okay, so we're going to have a mental health break. But that's it. So this is a little piece about random walks, and there's some nice things to solve. But it's a very interesting, randomness, all-pervasive business. I mean, noise, for example, in signals. We tend to think of it as bad, probably. You want to get rid of noise, but it can be kind of harnessed in interesting ways, which I think happens in biology, probably more than we suspect. This is just a ridiculous thing. This is just... All right, so that's a feel-good thing. Apparently is what that ridiculous thing does. Yeah. Looks like it's covered in dirt. Okay, all right. So it's just like, yeah, we're okay now. All right, so variable transformation. So this is an interesting thing. I've mentioned this a little bit before. So the idea is that you have a completely reasonable thing like an exponential distribution, which we can derive and explain for very simple. It's a failure model gets you that. We can get something like a Gaussian, again, fantastic story for why that is. And then there's some transformation of that variable that's distributed as a Gaussian or an exponential to some other variable. And that transformation, which again has a good story, gives you the weird distribution over here. So, okay, so that's what I'm saying. So we have elementary kinds of distributions. and then there's a power relationship between variables somewhere. So let's do it. We're going to do it in a kind of a general way, and then we'll have an example, which is known as Holtzmark's distribution. So we have a random variable. It's got some distribution. As I said, this is not a bad thing. It's got some finite variance, nothing crazy. And then there's some variable that's connected in another way. And so this is the general formula for connecting to the probability distribution of two variables. You want this to be true, right? So probability of y dy. So do I need to put in? Probably should have something extra there. Yeah, you're right. You can kind of ignore that. Maybe just ignore this line. So the probability that y equals y is, and if they're connected, so we know this distribution of x. So this is a weird, horrible looking thing, and we'll we'll do a practical example. But so there's an x in here. So if we can get we start with y and we go back to x. So that's the inverse function, right? We know there's a relationship between y and f. Right, because we really know the distribution of f, and we're transforming to y. So we have to use its inverse here, and then we're going to actually sum over all y such that the inverse of y is equal to x. Right? So given you want to find what the probability of y is, you have to see all the values of x that it could come from. This is a horrible looking little beast here, but this is actually just what we did. It's the Jacobian piece in here. Again, that's like the derivative, and this is really x in here. But this is all in terms of y now. Okay, so we'll do it by hand, and that will be a better thing, but that's actually the correct thing. Let's assume the relationship is 1-to-1, so we don't have this kind of messing around. And we'll do it for this particular example where there's some kind of power law relationship. So it's an inverse power law relationship is the structure, and this can have a very simple explanation. So we'll do it in the abstract, and then I'll give you an example. So let's think about what happens when y is large and x is small. So we're interested in large y. Again, it's the tail, right? What's the probability of y as we go out to very, very large y? So we have to do our little transformation between the differentials. So dy is d whatever y is in terms of x. So it's cx to the minus alpha. So we're going to differentiate this. We have our c here. Minus alpha comes down, x to the minus alpha minus 1. dx. Now this is pretty good. We want to bring this blob over here so we can get a form for dx. Okay, so we're going to invert it. So dx is, let's see, there's a c in minus alpha that's on the bottom. Put the minus sign up here. And then it's x to the alpha plus 1 dy. Yep. But this needs to be in terms of y. Right? So that little thing there is actually this little horrible beast here. Right? Okay. Sorry. So we need to put in what x is in terms of y. So if you invert this, it's y divided by c, and then to the power of minus 1 over alpha. So things getting a little nasty. So there's a y over c to the power of minus 1 over alpha. That's this bit. So there was an alpha plus 1. Now it's alpha plus 1 minus 1 over alpha. It's really exciting. There's a little magic madness, I suppose. So we've got our dx. So our dx actually, that's where all the goodness is happening, right? So it's about what happens to the Jacobian. So the dy is still here, but now we've got the power law appearing. It's really happening there. Y to the minus alpha plus 1 over alpha. So that's going to be in there. Okay, so this is just getting things that are constants and so on, right? So there's actually a minus c to the 1 over alpha. We can pull that c out and connect it there. There's an alpha on the bottom. And this is really what we have. Y to the minus 1 over alpha. Good. Okay, so we're going to make the transformation. It's going to look like this. So p of y dy is p of x dx. And here's our dx. It's this horrible blob here, constant. This is the big piece that's going to matter. It's y to the minus 1 over alpha. And then we're going to put what x is into p. So again, alpha is greater than 0. So when y is large, this number is becoming small. So if we're talking about a Gaussian, for example, right, the argument's becoming small. So this is all fine. There's nothing bad. The Gaussian has a nice behavior in the middle. And this will be the dominant piece. Right? So our distribution for y will be a power law decay, will be a -1, and then this -1 over alpha. So -1 is kind of the, well, it's not really true. -1 is sort of a base, I suppose, and then you can think, depending on the alpha in that transformation, how it's going to affect it. Okay, so let's say p of x goes to some constant as x approaches 0. Like I said, maybe for a normal distribution. Right, so this is x approaching 0, means y large. Then we get exactly this kind of form. So that's a very reasonable explanation. Right? We started with something that's, potentially we've started with something that's quite nice. So we'll see this in a couple of examples, not just in these slides, but later on when we get to robustness. If in fact though that x goes to 0 itself and it's x to the beta, so it's got something a little more interesting, that's okay too. It just means that this thing it'll be this to the power of beta, so y to the minus beta over alpha. You'll get another y piece. So we get y -1 over alpha, and then y to the minus beta over alpha. So you just get another term in your exponent. So exciting. It's just so exciting. All right. This is good. This is fine. This is a nice thing to have done. All right. Yeah. All right. Okay. All right. Let's have an example in a little bit. So if we had an exponential distribution, this is all good, normalized. It's not a bad thing. And we've got our transformation. We can just stick in the result. Then we'll simply get, again, this -1 over alpha. As x approaches 0, this thing just goes to 1 over lambda. Well behaved. We can talk about this maybe at another point, but exponentials you get out of randomness, so a random failure mechanism. So probably if something failing is p, probably if not failing is 1 minus p. What's the probability that it exists for n steps? You can figure out that gives you an exponential, so we'll get to that later. Okay, so this is good. Okay. So bad. I was going to show you this terribleness. All right, okay. I just wanted to show you a ridiculous thing, of course. This is hilarious. Just ridiculous. Right. Right, so this guy. Okay, so, which has made a comeback. So when I was a kid, I used to watch this particular character. And for some reason, I thought that in the desert in Australia, Daleks were going to come and kill me, which was really did terrify me, actually. Anyway, so also some other bad characters. But yeah, that never happened, as it turned out. Okay, so Holtzmark distribution is related to this because it's this silly idea. It's actually from a paper in about 1912. So you select a random point in the universe, which is a tough thing to do, unless you've got one of these things and you can't use it very well, and then measure the force of gravity and observe what the distribution is. So we're going to select. Of course, if you land in a star, it's all over for your random sampling process. But that never happens, I guess. It's not a good narrative continuation. F to the -5 really never happens. They never also, sometimes. They always seem to land on the planet's surface. So F to the -5 halves. So that's 2.5, right? So most of the time nothing happens, it's all good, you're fine, it's fun visiting space, and then you're in the middle of the sun. That's bad. Okay. So how do you get that distribution? So, I'm just going to give you some things these are all well-known things, right? Except for the space travel bit. So F is, so let's think about this. So matter, of course, is in the stars when we talk about the whole thing. And we've got all these interesting patterns out there. So it's distributed unevenly. And so let's think about this. So the probability of being from a distance from a single star, if you're randomly sampling, right? You're randomly sampling space. So you're randomly appearing these shells. So there's more chance of being in a shell further away. There's more points, okay? So locally, it's going to look like this. It's growing like r squared, which is the area of a shell, right? With a little dr, so that's the thickness of that thing. So a bit dubious, obviously. They're not really randomly distributed in space, but probably okay. So we're going to hack through this little, it's another back of the envelope thing. So we'll just think about what's happening at 1 star. We have the force of gravity, right? It's proportional to 1 over r squared, which, makes sense, right? Because it's decaying. So again, it's a surface story, right? So as you go further out, gravity is kind of abating. But apparently, I believe it's true that Newton, when he was messing around trying to do this, and when he wasn't working on astrology and all these other things he did, or thinking about making money, which is what he did after about 40, tried, I think, a bunch of things, like r squared, and, really odd things in retrospect. This is the monk death story. People, very, very smart people did in retrospect, very silly things. Anyway, this one works, and it has a very sense of, that the force decreases, and it decreases in this nice spatial way. All right, so we've got this probability for r, and now we have a connection between force and r, so we want to create the distribution for force. So we can turn these guys inside out. Now we have r is proportional to force and minus a half, so that's our minus alpha that we had from this explanation. So we can also do this. Well, we might as well work on df and dr squared. We want to get rid of the dr over here. So df is proportional to dr to the minus 2. So we get an r to the minus 3. It's constant. We're not worried. Dr. So dr is proportional to r cubed df. And we know r is f to the minus a half. So we get an f to the minus 3 halves df. And we have all these pieces, right? So this is the connection between them. This is the connection between the differentials. The Jacobian is this little beast. And probability is growing like r squared. Yeah. I mean, it's a hack of a thing. Obviously, you can't really normalize that. So P of f df, P of r dr. Then we have, let's put all these things together. We're going to put our P of r is this beast. We're going to put an r squared in there. We put this guy, so the dr is being replaced, so there's f to the minus 3 halves df. P of r, some constant f to the minus a half, so it's really r squared, so it's this power, f to the minus a half to the power of 2. I'm saying lots of words with numbers. So that's f to the minus 1, f to the minus 3 halves, so we get f to the minus 5 halves df. Okay, all right. That's a fun one. Obviously, there are lots of different other examples. Gamma is 5 halves. It's exactly this kind of story that I'm trying to tell you. The mean is finite, variance is infinite. It's what we would call a wild distribution. We went from a mild one to a wild one, kind of a mild one. So random sampling in space is usually okay, but it can end terribly, right? So that's it. In fact, so this, as we've said, the exponent between 2 and 3 is exactly the kind of exponent that lulls you into a false sense of security. You keep putting money into this investment, whatever it is, or you keep building houses in a particular place, and things can go horribly wrong. All right. This is, you should just ignore that. This, I'll show you just a little bit. This is pretty funny. This is from the 80s. This is a terrible song. That's great. Again, a mental health break, if I'm allowed that. This is, I don't know what happened here. This is... At some point we see that the... I have no idea why this was a very popular song in the 80s, which is not good for the 80s. Right, England, yeah, strange things. I think at some point we can see the creatures have feet, which is funny. Come on, show me. This is so wrong. Just one scene, and then I'll stop. That's it. I guess they just drive around in a police car. All right. Yeah, okay. Just for fun. All right. Okay. All right, last thing I want to say in this set of stuff, and then we'll get on to this the big fight between these two characters about generative mechanisms. So, PLIPLO, parallel law in, parallel law out. Now, it's okay to connect these things at times, but you shouldn't pat yourself on the back if you've explained some power law size distribution using another power law size distribution. So this happens. Okay, not allowed to do that. So sort of a homunculus argument, you know, like we have a little person inside us. Okay, so don't do that. You need mechanisms. And it can be hard. It can be very hard to see where some of these things come from. So, you know, from a molecular, the randomness thing is great, right? The diffusion thing, you know, this is Einstein 1905. We can really just, things bouncing off each other gives rise to Brownian motion. But the fractional stuff, which we absolutely observe, it can be harder to get that micro story. All right, so don't do that. That's a good spot to, and that's where we stop. All right. No Doctor Who fans. Okay, so part 2, we're going to move away from just mad randomness, which produces so much, to a really, really interesting story of rich gets richer, basically, right? So this is all pervasive, really, all pervading. And there's going to be this argument between these two characters, Herbert Simon, brilliant sort of polymath character who was at CMU and was actually in, some organizational science thing, but he's a early computer scientist character as well, did lots of things. And Mandelbrot, who's famous for the almond bread, famous for the fractal business, but he was one of the first people, for example, to notice that financial time series of fractal as well, to point that out in the 50s, I'm thinking. Anyway, these two had a bit of an interesting fight about where these certain kinds of power law size distributions come from. So we'll go through these. Simon's first, and then we'll get to the Mandelbrot. Okay. All right, so let's see. So we have, what we had before was additive aggregation. I'm going to call it that. No one else necessarily does it, but I'm going to call it that, just to kind of give some taxonomy here. So it's just, you have random addition and subtraction. You do have memory of just where you were, but no other memory than that. And the kind of thing we did was we compare against realizations, right? So you have this random walk, and then you have another random walk, and we're going to make a whole ensemble of them, and then look at all of those guys. But they're not competing against each other. So now we're actually going to, so for instance, this probability of first return, they're all separate pieces. So now we're going to have a whole ecology of things taking off at the same time or evolving at the same time, competing with each other. And it's going to, so competition comes in, and it's going to be, again, a kind of a random additive, but also copying, right? There's going to be copying involved. So replication. One can say that these, there are arguments made for how it might apply to all sorts of things. So words, sort of one of the great examples. The web itself, to some extent, so there's the internet and the web, right? Although everyone seems to call the web the internet, but they have different structures. Wealth, actually, productivity. There's productivity in science. So how many papers scientists produce? This is one of the 3 laws of bibliometrics, and it's dates from the 1910s, I think. Okay, there's that. Popularity, of course, books, people, why things take off. All right. A grave problem that we always have is with these power law things is there are just simply competing mechanisms. There are mechanisms themselves that can give rise to the same exponent, and then you can have all sorts of arguments about that. A lot of papers over the years have said, here's a mechanism, it gets the same exponent as the real data, and then now we're done. That turns out to be a bad thing, right? So you have to actually show that your mechanism is in the details of this, of how this system actually evolves. And that requires a lot more measurement. And I'll show you a couple of examples of where people have dug in and gotten to that level of detail. Okay, so later on we're going to have catchphrase evolution for how people describe these things, but I'll just give you a sequence of the work here. So there's Yule's work, and this was it was about evolution, and it's the number of species per genre. So this is, some per gen. So this is something that, of course, that we imposed back then. It's not DNA based, but this was our taxonomy of the world. So some genera have a ton of species, and some only have one, right? So that's the story. And again, a power law size distribution. Number of scientific papers per author, so that's Locke's law. So these are observations. There is a mathematical story in here. Then in order of time, yeah, actually it's Mandelbrot. These are academic works, analytic works where they're trying to explain it. Of course, in here we had 1949, we have Zipf with this business, right? And that inspires this work that comes in a few years after it. Mandelbrot has an optimality argument, so we'll look at that second. Right, and this is only about language, and the idea is language has evolved to be optimal in terms of its ability to communicate information. Very, very reasonable, plausible hypothesis. I really don't like hypotheses. I shouldn't have said it. All right, so that's my problem. Herbert Simon actually has this random growth model, and that's where we'll go first. But had a more general view, talked about word frequency, city size, income, so wealth, well, income I should say, publications and species per gen. So he sort of really laid it out as an incredibly general model. And then this is an interesting thing. So the DeSola Price produced, so this is a fellow working in information science, produced a body of work, these particular papers here, about how citation networks were structured. Now, of course, this is difficult work because you had to go to the library and document the whole thing. Of course, in the last, whatever it is, 15, 20 years, with the web, we've been able to make this great transition, really, in terms of indexing knowledge, so you can look at a paper and see what's been cited by it, right? That's hard. If you're sitting in a library and you pull out a paper and you say, I wonder which paper cited this, that is horrible, right? It'll tell you which ones it cited. That's its job. But the other way, awful. So obviously lots of graduate students suffered, possibly perished in stacks doing the job. Sorry, people, that's it, yeah. They're mentioned on page 20, It's true. I mean, it's true. It's absolutely, especially in the social sciences, it used to be, there's one author, and then it sort of slowly becomes clear, on page 7 and 12, that someone did all the math, someone collected all the data, and they're sort of mentioned in a footnote, Thank you to the graduate student. I can't remember their name. There were maybe 3 of them that helped me, Anyway, so now we are, and I think more people are a little better about acknowledging other humans. It's kind of nice in sociology when they're asocial. Okay, so sort of true. So let's see. So we've got this build. So here we go. This is networks. So now we have networks. And then this work becomes somewhat forgotten or not known very generally, and we get to the web. The web appears. So that's an interesting thing. And we have Barabasi-Elvin, and this is a giantly influential piece of work. We'll come to it later on. But these things are deeply related. DeSola Price draws directly on Simon. The citations are explicit. But takes Simon's model, which is not about networks, and turns it into a network model, right? So you can think about a network evolving, nodes that have lots of friends, web pages that have lots of other web pages pointing to them, get richer, right? It's a rich gets richer story. So the more you have already, the more you will get. And we'll talk about that because it comes from the Bible, which is funny. Not the Bible in general, sorry.
Now that Google Scholar and stuff mostly return things by the article with most citations first, is it accelerated this process?
Yeah, and so I don't know, I don't have data on that, but that is one thing you have to worry about tremendously. Yeah, anything that's a top 10 list or anything like that accentuates the rich gets richer for sure, absolutely. If you make it easy to search, and I'll show you a experiment we did years ago, which absolutely gets at this. Yeah. So that's a great question. So you want, in some ways, to present. You do want to present that. You want to present that information, but you want to be able to throw up something too, like here's not just random, but here's something that's, here are the really different groups or something that cited it, something like that. You need some other, we talk about filter bubbles now, but that's been a problem for years, and that's something we, acknowledged a long time ago in our work. So, yeah, really a good point. So, all right, yeah, so there are different levels of rich gets richer, and of course there's, we do worry at one limit, which is the monopoly, right? We don't like monopolies, or at least we tend not to. So we have laws about that and so on, generally in the Western world. But you can have near monopolies or complicated kind of ones with networks. So we'll come back to this later on, but I just want to say that this is a kind of a quirky example for Zipf's law. We've talked about some others. This is something that I haven't shown. This is actually 2008, it's Physical Review Letters. This is the number of links into modules, should I say that word? Into packages, and it's for Linux, right? So you've got all these little packages, and this one depends on this one depends on this one, and it's just like most software. It has a somewhat biological aspect to it. There's sort of literally kernels and so on, but there are essential pieces that all the others use. And that tends to have, there are some that have many, many links. There are many that have just a few links. And so this is a good example of a Zipf's law story. And the nice thing about this, we'll come back to it later on, is that you can study the evolution of it. You just simply have the evolution of, in this case it's Debian, and they name their pieces after Toy Story, right? There's Woody, Sarge, Etch, and Lenny. Right. Okay, so first of all, there's some, this is recent, it's 2008, right? So this is recent work. That's probably the best piece. Okay, so this starts in the 50s. I think that's the strongest piece up until that point, or really the first major piece that looked at the mechanism, like really got into the details. So that's a long time, 50 years, Made all the more amusing because of the arguments these guys had. All right, so as I said, he's a very interesting character. So one might call him a political scientist. He did win a Nobel in economics, which is a bit surprising, but all these things, cognitive psychology, computer science, wrote a lot about organizations and administration, produced a few of these words or terms that we use, bounded rationality and satisficing. I mean, very much in the genre of, or in the tradition of economics, they're not very nice words, like network externality. But this satisficing is the idea that you're happy with something, you take it, you don't compare to everything, right? So it's versus optimizing, which a lot of simple economic theories might presume, right? That everyone has perfect knowledge, and this is this is saying the same thing, right? You're rational, but you don't know everything. About 1,000 publications. He did all sorts of things. He was in, cybernetics was the word they were using, but he talked about complexity a lot. Lots of things, and wrote these great books. Yeah, so Nobel laureate, which is good. All right, so let's start off on this business. I had a problem where I thought I'd said elephant, but I hadn't, and so now I'm saying elephant anyway. All right, so you probably should think of elements. So we have an elephant that has a particular flavor at t equals 1. Sorry. So that's just what's going to happen. Here's our mechanism, very simple. So we have one comes in the room, obviously need a big room. It's got a particular flavor, color, something. And then we're just going to have a clock, and at every time, we're going to add a new elephant in one of two ways. So it will come in the door, right? So obviously it's getting messy. And with probability rho, your elephant will be have a new flavor. Okay, very simple. So you can imagine this is all sorts of general things. For some reason it's elephants. So with probably 1 minus rho, the elephant looks at all the ones that exist and copies one. Says, I want to be like that guy. Okay. Because it's not a very brave elephant. Okay, so, and that's this is, you can see the human part here, right? Okay, so rho is typically small, the brave ones, or they maybe just make a terrible mistake and turn chartreuse instead of whatever the colors that are already there. So elephants of the same flavor form a group. So these groups are starting to get bigger. The important thing is you are randomly choosing. You're not choosing from groups. This is a problem we'll come to. You're not choosing from groups. You're just choosing randomly from the elephants, right? So it doesn't matter if there's a group of, all right, well, I'll have an example. So let's look at generally what these two pieces are. This is mutation and innovation. Think of it like that. New thing comes along, still an elephant. And this is replication imitation. So you've got these two parts of the mechanism. So, and we'll come back to this, I suppose, but you can see at the limits, we've probably, if rho is 0, there's no innovation, then elephants just copy that first one, and they're all the same. Okay, so that's well, I mean, that can happen. Everything's exactly the same. And for rho equals 1, they're all different, right? So they're our endpoints, right? They're all different flavors. Okay, so let's see what happens in between. So this is not how you write a book, but it might be roughly how you might create a language slowly. So words appear sequentially. With probably rho, the next word has not previously appeared. So you can imagine you're reading through Moby Dick, you're really suffering, because that's what it's about. And then you're 30 pages in, you've got all these words, and then you just randomly choose a word. You're Herman Melville. You're writing the book. So you're writing the book, you've been spending some time in Nantucket, and for some reason you use this approach. 30 pages in, instead of choosing the next word in a good way, you actually just randomly choose a word from before and put that in. And then you move on. And with probably rho, you make a new word. And with probably 1 minus rho, you just go and randomly choose a word from before and put it in. That's a bad plan. But that's the idea. But you can imagine a language where you start off with ook, 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 and then maybe you start saying some others. So 1 minus rho is, randomly choose a word that exists from before. Again, mutation, innovation versus replication. This is not a good way to write a book. Okay, so here's a little example at some point. So we've had 21 words have appeared. Let's look at what would happen in the next time step. So lots of ooks. So it looks like we start off with ook, right? That was kind of the first word, got repeated a bunch of times. The next word, a proto word comes in and wants to be a word, and it decides. So then our next word appears. It's kind of coming in here. And with probability rho, it's just a new word, right? It's just a completely new word. And with probably 1 minus rho, it picks randomly from these words. And so the grouping is deceptive because it will just randomly pick from these words, right? But because of the grouping, that does then mean that there's a 6 in 21 chance that will be an ook. There's a 3 in 21 chance it will be an and so on, right? So that's what we've got here. So mechanism makes sense. Very simple. Eminently solvable, which is good. Yeah? So we have growth and we have a competition between the words. And it's good to be one of the words, so it should be clear that it's good to be, there's a first mover kind of advantage if you want to use those words. It's good to be early on, right? Yeah? So if you've got 10,000 words in your novel and you decide to be something new, good luck, Okay. So it has that. So it's a rich gets richer story. There's a the rich get much richer story, and the rich get a little bit richer story as well. We can vary to those. So competition is completely random between the individual elephants, right, at the individual level. But competition between the groups is not random. So that's just sort of, you get that for free, that the group competition is not random. You can talk about size bias, very natural kind of thing. So that's nice, because if you had to do, there are two pieces. If you thought about groups, you'd have to know, right? You'd have to get back here, and you're the new word. You'd have to write down there are 2 penguins, there's 1 duck. You'd have to write it all down, divide it by the number, then roll a 21-sided die, because you have them. You roll one of those, and then change to that word. Now that's not. So it sounds easy. Random selection sounds easy, but you kind of need something else. You need a way to bump into a word randomly. Right, we'll get to this later on, but it sort of gives you the sense that you don't need a great knowledge of the system, but you do need something that randomly gets at words, or whatever it is, elephants. A bit tricky. And so if you had to do groups, yeah. So you could also, all right, so the city version is, your friend moves, someone in Pittsburgh, so you're going to move there, or someone in Seattle, you're going to move there. There's some, right, you can imagine immigration working a little bit like this, maybe. and why bigger cities have a bigger chance of growing more. Someone can give these arguments. Obviously, it's a very idealized mechanism, and that's good. We can solve it, and we can then go and look at how it's wrong in various ways. So, a couple of pieces. We're just growing. The number of elephants just grows linearly. We could change that. The rate at which we get distinct flavors is simply the probability of nucleating a new flavor. After t time steps, we'll have rho times t, roughly, rho times t distinct flavors. Right, so rho is quite small, it's 0.01, say. Then after time t, we'll have 0.01 times t distinct groups. So we can immediately calculate that. You can add all sorts of other things. Elephants, for some reason, get eliminated. Those are bad. That doesn't feel good. They move between groups. You can have that. So as I'm sort of saying, you can elaborate this in all sorts of ways. You can have the innovation rate varying, which actually is really true for books, if you want to think about text. That's an interesting piece of work. But we're not going to worry about these things. I'm just saying some kind of obvious ones. You could change the way the selection works based on group size, right? So you could have the rich get much richer. You could have it proportional to group size squared, for example. It's harder to see how that mechanism can be manifested. Proportional to group size, or equal to, proportional to group size is easy because we can do it through just randomly choosing an elephant and copying that, right? So if we do random selection, we get linearly proportional to group size. But if you want it to be to the power of 2, then you have to have your elephant come in and use its abacus or whatever, or its Mac. Okay. It's got an iPhone. Use an iPhone. Okay. With a trunk. Probably pretty good. Okay, so as I said, mechanism for solution is not so easy. Okay, so what we'll do on Tuesday is go through the analysis of this beast and at the start of it. Then we'll get into what happens when we meet Mandelbrot, and that's an optimization story. So as you can see, purely random mechanism, you can think about it, just a random growth thing. There will be gamma functions, because that's fun. Some other little beasts, maybe a beta function, and which sounds surprising. And then we'll get to optimization and see how that works out. There can only be one theory, is important. Another great 1980s film is Highlander, and that will feature heavily. All right, okay. All right, people, thank you.